start back up. All right, let's go to the chalkboard. Okay, so far we've seen, what we've seen is, oops. So far what we saw was that the electric potential, electric fields pointed in the direction of decreasing potential. V high, V low. Okay. Now, so we define this scalar valued function. Okay. So the question is, what does this mean? So what this function means is it associates with every point x, y, z, it associates a scalar value. So for instance, at this point, it's 100 volts, 101 volt, 102 volts, and so on. At this point, it's 98 volts, and so on, okay? And you can evaluate the value of the function at every point. Okay, so now let's ask the following question. Okay, we want to know at any given location, we want to know, and in which direction does the function increase the fastest? Does it increase the fastest in this direction, this direction, this direction, that direction? Okay, so if you ask the question, the direction in which it increases the fastest and the rate of increase in that direction, that is what the gradient of the function gives. Okay. Okay, so the gradient of the function gives you the direction in which V increases the fastest, as well as the rate at which it increases. At which it changes, okay? So since the gradient is a derivative, okay, this tells you the direction in which it's increasing the fastest and at what rate is it increasing. Since this is a spatial derivative, it gives you so this function gives you the rate of change of voltage per meter. Okay, so the units would be volts per meter. Okay, so now let's do an example. So let's, I'm going to just make up a function v x, y, z equal to x squared y cubed z to the power 4. Okay, so we'll just do that function, okay? And the gradient v x, y, z is defined as del v by del x I. So the x component of the gradient vector is the partial derivative of v with respect to x I plus del v by del y j plus del v by del z k. Okay, so that's the definition of the gradient. And so for this example, for our example, del v by del x is, you're taking the partial derivative of this function with respect to x. And when you take partial derivatives, you're treating y and z as constants. So del v by del x would be 2x y cubed z to the power 4 I plus del v by del y would be, you're taking the partial derivative of this. So you're treating these guys constants. And that would be 3x squared y squared z to the power 4j plus partial derivative of this with respect to z is You're treating these two constants. It's 4x squared y cubed z cubed. Okay. Okay. So there's your gradient vector. Okay. And so now you can evaluate it at any point, and that will give you the rate at which it's increasing, and also the direction of this vector tells you the direction in which the rate is the greatest. The rate of change is the greatest. So that's what the gradient operator does. And by the way, just to give you what does the partial derivatives mean? So if here's the x, y, z axis, partial derivatives. So del v by del x tells you how the function changes if you move along the x-axis. Del v by del y would tell you how the function changed if you, this is what del v by del y would be. Okay, it tells you the change along the y-axis, and of course now you guessed, this tells you del v by del z. How does the function change as you move along the z-axis from any point? Okay. All right, so now you defined the scalar valued function. At any point you calculated the gradient, let's say, so the gradient of v, x, y, z. And what you find is the electric field at that point is negative of the gradient. So there's the gradient, and there is the electric field, a vector in the opposite direction. Okay. And that's what this slide is showing you. Okay, so here's the general expression for change in V is this line integral along any path. And now you take an infinitesimal change, so the small change dV equal to just that for a small displacement, infinitesimal displacement. You see in calculus dV is del V. If V depends on 3 variables, then change in V is del V by del X times dx plus del V by del Y times dy plus del V by del C times dz. So that's dV. And you can take the dot product of these two vectors, which is that ex dx, ey dy. And so if you equate coefficients of dx, dy, and dz, what you find is ex is minus del v by del x, ey is del v by del z, and ez is del v by del z. So the electric field is the negative of the gradient of the electric potential. Okay. All right, so that's what that is. And so now you know the meaning of a gradient function. The gradient function tells you the fastest rate of increase of that scalar valued function. Okay, and the electric field points in the opposite direction. All right, so that's what these graphs show you. So the dotted blue lines are equipotential surfaces. So this is for a constant electric field, and the potential is decreasing in that direction, and the electric field is pointing in that direction. So the gradient would give you point in that direction. Again, those blue dotted circles are equipotential surfaces, and the yellow-brown lines are the electric field vectors. Okay. So electric field lines are perpendicular to equipotential surfaces and point in the direction of decreasing potential. So V was, so we saw that V was electric potential. And if you have 2-point charges, then there's the potential energy associated with the 2-point charges. And the potential energy associated with the 2-point charges is given by that. Okay, so potential energy associated with the 2-point charges is given by this. So if the charges are opposite, then the potential energy would be negative. If the charges are like charges, they're either both negative or positive, then the potential energy will be positive. So here's the potential energy of a constellation of charges. It's just the sum of the potential energy due to independent pairs, okay, and so on. Okay. So this was the electrostatic precipitator that we saw in the last chapter as well. Okay, so this is smoke without an electrostatic precipitator working or in place. And if you turn on the electrostatic precipitator, you can remove all almost all particulate matter, over 90% of the particulate matter, actually close to 99%. So here's a large metal chamber. Here's the dirty smoke going in. What you have is a thin wire hanging in the middle where you have it, and the wire is at close to 100,000 volts. So here's 100,000 volts that you connect between the housing, the metal housing, and the central wire. And when the wire is at that large voltage, it easily loses electrons. And so it's spitting out electrons, and these particulate matter electrons will attach to these particulate matters. And since the housing is positive, the negatively charged particle, the smoke particles will stick to the housing. Okay. And so now you have clean air going out. And once you have enough particulate matter sticking to this thing, every once in a while you shake the housing and the dirt falls down. All right, now that we have talked about various concepts in electrostatics, now is a good time to talk about an electric car. In particular, we can talk about Tesla. So one of their models, S models, essentially the different models are different battery sizes. Okay, so the S model, I believe, comes with the battery size of 53 kilowatt hour. Kilowatt hour is a unit of energy. So that's the maximum energy you can store in that battery. Okay. So kilowatt means 1,000 watts. So you can get 1,000 watts out of that battery for 1 hour. That's what that energy unit means. Okay. So we'll do some numbers. A typical gasoline powered car can store about 12 gallons, and a gallon is roughly 4 liters. It's 3.75 liters. So, but anyway, we'll say 4 liters. 12 times 4 is 48 liters. So roughly, a gasoline powered car can store 50 liters of gasoline. All right. So here's a fully charged Tesla that has stored that much energy. And here's a full tank of gasoline with 50 liters of gas. And when you burn gasoline, you get, per liter, you get 35 megajoules of energy. All right. Let's say you drive around in your Tesla and you discharge it 60%. So you used 60% of that, 114 megajoules. Okay, so here's the conversion, 53 kilowatt hours. 1 kilowatt is 1,000 watts. So, okay, and 1 hour is 3,600 seconds. So you can go through the calculations. Okay, so what you're saying is when you use up 60% of your charge on the car, you've used up 114 megajoules of energy, which was converted into the motion of the car. For gasoline, let's say you use up your full tank of gasoline, 50 liters, that many megajoules per liter. So it's 1750 megajoules. So look at this. For the electric car, if you use a little over half the power stored in the battery, you've used up 115 megajoules of energy. And here it's 1700 megajoules. So that's a factor of 15. So what gives? Okay. Nowadays, Teslas have a similar range to the gasoline powered car. It turns out that the electric motor is about 90% efficient. So it's able to convert 90% of the electrical energy into mechanical energy. So 90% of that is, so this much energy in motion is what you got out. A gasoline engine converts only 20% of the heat released into motion. Okay, and so you see the gasoline engine is able to convert only that portion of this energy into motion, and those are comparable. So this is with 100% gasoline use, this is about 50% gasoline use, so you double that and all that kind of stuff. Anyway, so that's how they're comparable. And of course, the reason we are going toward that is because this guy has a large carbon footprint, and if you were charging your battery from solar cells, this would be a zero operational carbon footprint. Okay, the manufacturing carbon footprint presumably is the same for both cars. Okay, and really the operational carbon footprint is much larger than the manufacturing carbon footprint. So that's the whole idea. Okay. Van de Graaff generator stores charge on a metal sphere like this. Okay. And so it can store a large amount of charge. This is essentially a capacitor, and the charge is useful. Can be used for a bunch of things, to do a bunch of experiments. Okay, and the idea is the following. So you have a rubber belt like this, and the rubber belt rotates. You make the rubber belt rotate, and you have sharp brushes brushing against the rubber belt, and what that does is it charges the rubber belt, and since the rubber is insulating, the charges do not go anywhere. The rubber belt got charged here, and that charge is transported up, and that charge is transferred to this metal sphere via via connection. And now the belt has lost its charge. It comes back, it's charged again, the charge is transferred there, and so, and this uncharged belt comes down. And so by doing this, what you're doing is you're converting mechanical energy into electrical energy. Okay, and that's a Van de Graaff generator. So the sphere can be charged to quite a high voltage. Van de Graaff generator is a device that creates high electric potentials. It can produce electric potentials up to tens of millions of volts. Okay. So the larger the potential you want, the bigger the sphere needs to be. Okay. All right, that covers the topics from this chapter. And we'll stop, but before we do that, let me go over the slides and summarize some of the concepts. So summarize this chapter again. Okay. So we saw okay, so what this chapter was something called electric potential. So what we were saying was, let's say if you have a bunch of charges distributed, these charges will produce an electric field in this region. And we were interested in knowing this electric field in this region. Okay. And oops. Okay, yeah. So here we go. So you had a bunch of charges that created an electric field in this region. We wanted to know the electric field in this region. To specify this electric field is a vector valued function. You'd have to specify these three functions. Okay. So in this chapter, what we learned was, instead, if you can specify just the scalar function, something called electric potential, instead of specifying these three functions, all you need to do is specify V, X, Y, Z in this region. If you specify that function from this scalar electric potential, you can take the gradient of that electric potential, that will give you the electric field. And that was the punchline of this chapter. So instead of having to specify these three functions, if all you have to do is specify this one scalar valued function, and you can calculate the electric field from it. Okay. And this guy is called the electric potential, and that's only possible for certain types of electric field. These fields are called conservative electric fields. Okay. And that was the point of the chapter. All right, guys, so that finishes this chapter. I'm going to stop recording.